All right, cool. So, I had a few comments about this title. You don't like monitoring tools? What's wrong with monitoring tools? So I'm going to explain that a little bit, but first of all, thanks very much for inviting me to come up and open this conference up. It's always interesting to be opening keynote. You can either, if you go to a conference, it's nice to either be right at the beginning where you sort of set a whole bunch of things that people are going to talk about during the conference, or maybe somewhere in the second day so you can see what everyone's talking about on the first day and sort of update your stuff to react to that. First of all, most of you know me as the Netflix guy, but this is what I've really been doing the last few years. I've been out doing lots of talks and baffling people, and I adopted the Cloudicorn because Netflix was this weird unicorn that no one was ever going to have to want to copy that. And what happened over the last few years is people started trying to copy what Netflix was doing, and so we've moved to this situation, which is known as the Wardley no chart. This is enterprise IT versus everyone else. EnterpriseITadoption.com, you actually can go pull up a copy of this. But what happened is, basically with all of the IT cloud stuff, I'm on that green line, and the rest of IT was over there. Now everyone is desperately trying to figure out how to do cloud. So I'm now, the reason I joined Battery Ventures is I'm now trying to bridge that gap for people. And that's actually why my fun new job is to try and explain all this I said no damn it level stuff, whereas everyone is now past the oh fuck point, and they're all doing it. So why am I at Monitorama, given that I'm sort of mostly known as a cloud guy? Well, I've got about 20 years of work and history in sort of monitoring and open source. So about 20 years ago, I wrote something called the SE Toolkit, or contributed to it with Rich Pettit. Did a book which a lot of people got on some performance tuning. Wrote some more books, most about monitoring tools and basically about how to manage Solaris better. And then we used to go to the CNG meetings, and I got on there at some point. And then I had this capacity planning with free tools workshop that we gave several years at there. And those slides are up on my SlideShare, one of my older slide decks, and I'm here. So what did the world look like in 2008? This was kind of the state of the art for free and open source tools. This was my kind of summary slide. Some of those tools you recognize the name, they're still around. But that was, three-tier monitoring, sort of small number of machines, and people trying to figure out how to deal with this. And the idea you could do this with open source tools was at the time fairly subversive. This was people going, no, you really have to go pay real money to do this stuff. Those of you who didn't know what the SE Toolkit was, this is an interesting approach that I haven't seen taken up, so maybe this will inspire some people. It's a C interpreter that knew how to get all of the metrics out of Solaris in a pre-digested form, so you could just write the script. So VMstat was just a one-liner script that said, well, I want to pull this data and I want to print it in this format. And if I want to do something interesting, rather than just printing it, I could do anything I wanted with that data. So we've got a whole slew of tools. The resolution is not good enough to see them, but these slides will be up at some point so you can go see it. And I built this virtual Adrian script, and I heard recently this is still running on some large machines at some large well-known sites. Anyone that's running a big Solaris machine probably still has a copy of virtual Adrian running, which is kind of a scary thought, considering it was written because I was going to go on vacation one summer, and people used to email me bits of IOStat and VMstat and ask me what I thought, and I says, well, I'm going to create a script that does that you can run while I'm not there. So anyway, it still has a few things in there that I haven't seen other people adopt very much. Most people still don't get that interesting. So I've got two sets of topics today. So first I'm going to explain what I meant by the title, and then I'm going to talk about some challenges for monitoring in this area. So continuous delivery microservices, what does that do? So closed loop control systems, tools aimed at developers who operate code in production, and then the sort of dynamic cloud-based application things. So what did I mean by no more monitoring tools? Well, we have too many of them already, and what I really want is more analysis tools. So maybe we should call this Analysis-Rama or something? Would that be, is there one? So I'm just going to throw up some rules. So this is my basic rule here. I've seen too many people, building a monitoring tool, and by the time they finish getting the data out of your machine, storing it somewhere, and generating a graph, they sort of collapse, exhausted, declare victory, and move on. And that's, the problem is just staring at a graph doesn't solve problems. What I'd like that to be is like less than half the work. I want people to spend a lot more time on analyzing, making sense of metrics so that the system actually tells you something you didn't know or has feedback control loops in it. So it's actually managing, dynamically controlling systems. As we build more and more automation into systems, the monitoring is part of a feedback loop, so it's no longer this add-on, tacked-on thing that's just telling you maybe it's working or not. It's part of the whole system. So that's really what I meant there. I mean, we probably still need to build some more monitoring tools, but I really want people to spend a lot more time thinking about how they're using the data and how they're analyzing it better. All right. So what's wrong with minutes? So let's try and explain this. So let's say this black line on this graph is something happening that went wrong. Something broke at whatever, 2 minutes 20 point in this thing. The yellowy line is a threshold, and you're looking for the metric, which is the purpley line, and each of the points on it is 1 minute apart. So the first measurement interval, there was 20 seconds before the failure, 40 seconds after, and it didn't quite cross the threshold, so it didn't even trigger. The next one, okay, now we're finally at the instance, at the place where it's being measured, you now have a value that's higher than your threshold, but it's still on the instance, you can't see it yet. So a minute later, generally the 1 minute monitoring systems, it takes about, they gather data from all the machines, and a minute later it's actually arrived at the central place where you collect all your data, and it's being sort of marshaled and processed. Maybe sometimes some systems take several minutes to process their metrics. And then maybe a few minutes later, the user looking at a graph sees a metric move, right? The first metric that actually is above the threshold or the monitoring system. But one metric isn't usually enough to say something bad happened. You need several. So maybe sort of 3 data points in the bad space is enough to trigger something. So you've got about 8 minutes, 5 to 8 minutes of delay after something bad happened. And let's say you just pushed some code or changed a variable and broke something. Whoops, I didn't mean that. And then you go to revert, you change back to the previous code, or you change the configuration variable back, and then you sit and wait for another 5 to 10 minutes to see if it actually fixed it. And the problem here is, 10, 20 minutes of outage happens for something where you just flipped a bit wrong, flipped the configuration thing wrong. But if you could do that in 5 seconds, if you could see it in 5 seconds and revert in 5 seconds, no one really cares about a 10-second outage. They don't even notice. It's within a browser refresh time, retry time limit, right? So what does it look like? It's the same thing, except I didn't, this is 1 second update, so it's measurable in a second, and you basically, within like 5 seconds, you can actually see that something's happened. Why does this matter? And what's driving this is continuous delivery and the DevOps automation. So changes are supposed to be much more frequent, but much smaller. But they are also, individual changes are more likely to break something because they're going through a much shorter test cycle, but then they're revertible. So you want to be able to push stuff out incredibly quickly, but notice that it broke and revert it really, really quickly. And if the cost of failure is small enough, meaning that you can tell it broke and roll back in seconds, then you're doing fine. And you can actually get much more aggressive on rollout. And this is kind of the current state of the art. That's sort of the way Netflix operates. It's the way a lot of people doing continuous delivery operate. So this is kind of a new sort of demand coming from this developer agility place. So there's a couple of products that do things in seconds, Uber Cortex and Boundary. These are SaaS-based services that will gather data on a 1 second interval and report it and do analytics on a 1 second interval. And they typically take 5 to 10 seconds of latency, because there's quite a lot of processing going on in the SaaS-based backend. The way Netflix does this typically is using Hystrix and Turbine. This is interesting because on your front end, or on the machine that you're monitoring, that you're about to push code to or turn something on, you open a browser that connects directly to it, and it opens a WebSocket and is pushing JSON straight back into your browser. So there's nothing between you and the service. Turbine is an aggregator that takes all of the members of a service and just flows through all of these JSON objects and aggregates them and spits them through, so it's just a straight flow through. So the latency here is, actually when they first ran it, it was doing about 10 updates a second, and they decided that was a bit excessive because you couldn't really see what was happening at that speed. So they slowed it down to once a second. And you get 10, 15 seconds worth of history. And if a circuit breaker flips and something breaks, say this thing here at the bottom right broke, it goes red and the circuit breaker's open, you can tell that this is the thing that broke, and it's usually one of the dependencies of your system. So if you're looking at the front end, you see this dependency that I'm trying to call broke. And then you call whoever owns that dependency, and PagerDuty goes and things fire off and whatever. So there's ways of doing this. So this is, I've got rule 2. I'm going to go through 5 rules here. So rule 2, I want the metric to display latency to be less than what I call human attention span of roughly 10 seconds. If I push a button, I'll maybe wait 10 seconds to see what happened. I'm not going to wait 10 minutes. I'll have gone and got a cup of coffee, forgotten about it, and the site will be down. That's the kind of problem. All right, so moving on. So what's wrong with milliseconds? Thinking about different things here. So what I care about here is that a lot of the JVM-based metrics, the unit is milliseconds, meaning that it's an integer number of milliseconds is used to measure time, and it's just not accurate enough. You can do a round-trip network with less than a millisecond. Disk access latency is less than a millisecond, and apps can respond in less than a millisecond. So there's too much rounding here, quantization, and I saw errors on our system that says Cassandra's latency is 1, which is higher than 0 by an infinite number of standard deviations. Therefore, it would fire all these automatic alerts. So that wasn't good. So I finally kind of beat the vendors into adding nanosecond resolution times and not using milliseconds. So that's kind of a nit, really. Most people don't have that problem, but if you're measuring time, don't use integer milliseconds. So the rule here is validate your measurement system has enough accuracy and precision. And if you're using it for closed-loop feedback, you really need to have like a control systems or a measurement systems analysis approach. And there's something called ANOVA gauge R&R, which if you don't know what it is, I put a link there on the slide. You can go, actually, there's a whole science of measurement system, validation and analysis, which you can use to guarantee that you've actually got the properties you need. And particularly if you're doing some feedback, closed-loop feedback, you don't want to have brokenness in your measuring system. All right, the next one was monoliths. So I don't like monoliths. So this is the problem. Simple to build and install. You build yourself a monolithic monitoring tool, and then it goes down, and then you're blind and you can't see what's happening. And then maybe in the old days where you wrote changes to production happened every few weeks and stuff just sat there and wasn't changing, that was okay. But when continuous delivery, you're doing tens of updates a day, you have to see every single update. If there's any downtime, you've got a problem. And if you're feeding stuff back in a control system, you've got gaps in the measurements, everything's going to be broken. So your monitoring system needs to look like this. You've got to have a pool of aggregators for collecting data, a pool of systems for displaying it, and you could have a lot more of the blue things you're monitoring here. But you shouldn't have any one monolithic place that if it goes down, your monitoring system stops. That's my point. So I can lose a couple of systems and everything still works. I can upgrade systems. If you've got a monolithic operating system, you want to update it, you have to take it down usually. So the problems here are scaling, data collection, analysis, reporting, throughput. You get limits on the number of metrics can be collected, so that blows up occasionally, takes out your monitoring system, or traffic storms caused by large numbers of machines suddenly appearing, because machines are coming and going much more often in this kind of environment. And gaps in the metric history, whoever is using it say, why is this gap? Does that mean my service went down, or does it mean the monitoring system went down? If you can't tell the difference between those two, then you lose confidence in the system. Eventually someone goes finds a new monitoring system. And so you can think about this as how do you want to build your monitoring system. It's really what I call in-band monitoring, meaning let's say you're in a cloud or in a data center, your monitoring system's running in the same data center or in the same environment as the thing it's monitoring. And that's convenient, it's low cost, it's efficient, you can gather lots of data. But if you get an outage, your monitoring system quite often goes down at the same time as the thing it's monitoring, which is really, really annoying, because then you're not quite sure if your thing is still up or down, and when you're trying to bring it all back up, you're doing everything blind. The nice thing about SaaS-based monitoring is it's often a totally separate world, and quite often it can tell you, no, your system is still up, it was your monitoring system that failed, or something broke, but you really have a service here. But then, the SaaS-based service is usually run by somebody else, and that thing goes down too. But what you really want is to have both running, and then it's very unlikely that the one outage will take out both, whatever's monitoring externally plus internally. And this, if you really want highly available monitoring, you want to have two independent systems monitoring it. This is maybe more work than you want to do, but maybe you can have these things can be monitoring different kinds of things, but there's enough overlap that you can tell that everything is still up. The basic point I'm trying to get at here, from before roll, the monitoring systems really need to be more available and scalable than the systems they're monitoring. And that's a fairly high bar to set, but again, once you do this, then you get a high adoption rate of whatever system you put in, and you can use it for things like monitoring and feedback and those kinds of things. If it's less reliable and available, then you're not going to rely on that thing to control everything. So let's look at continuous delivery. You've got a very high rate of change going on. Code pushes cause floods of new instances, metrics. The way Netflix does it, launching 500 new machines is like a daily occurrence or several times a day occurrence. And then you've got these baselines. You're trying to figure out whether something unusual happened, but everything is changing so fast that you don't have a baseline. You can't build up a baseline of what's normal, so everything looks unusual. So your monitoring, your alerting algorithms are firing all the time, so they've never seen this thing before, because something's just turned up. And then it makes it hard to generate, what was my actual usage over the last, 6 months? Well, that's, several thousand code pushes, so how do you aggregate across those things? And then the other thing is if every time you get an update in production, you have to go in and hand tweak something in the tool to configure it or manage it or set it up or set thresholds on it, then you'll go crazy because you can't do that several times a day. And your monitoring then generates this kind of bit rot where it gradually gets less and less useful. So everything has to be automated and everything has to automatically discover what's going on. Again, this is quite a challenge and something that I spent a lot of time at Netflix kind of working on trying to get these things to be done right. And then we're moving to microservices. So instead of the applications being monolith, they now are made up of hundreds of different services, and they have a complex flow of requests between them. So how many services really? This is from a presentation at Guild Group. I don't have the actual access here, but this is like weeks or something along the bottom. And they moved to microservices, and they went from a handful of services to 450 services over 6 months or a year or something like that. And that sounds like quite a lot of services to monitor if your system. How do you configure monitoring a service if there are hundreds of them? So they have this architecture diagram for part of this, and this is for 12 of these services. This is actually a boundary network monitoring plot. This is from the same presentation slide deck by Guild Group. And I call this the Death Star because this is actually a simplified version. This is actually the Netflix utility. You get all of your services, arrange them in a circle, draw lines between them, and you can no longer see what's going on. This is the architecture diagram. I think Groupon have exactly the same diagram as well. So anyway. Yeah, so that was a very simplified one for Guild. They didn't have a full 450 slide one. So that's part of the problem. So one of the challenges is how do you visualize these things? And there's some internal tools being built at Netflix at the moment to try and do a better job of visualizing this. But you have to build hierarchy into your visualization. You've got to start grouping things together. So now you don't just have services, you have groups of services, and you have to think about how they're distributed, and you've got to come up with some interesting visualizations. So this isn't just like drawing a bunch of strip graphs. Right? How do you do, when there's 400, 500, 600 services, you're overwhelmed with strip graphs. You've got to make some more sense of it. And this, I think, is kind of the bleeding edge of, I'm really looking for some interesting visualizations in this space. And there are a few people working in this area. So a little bit on control systems. Feeding stuff back. So this is actually the old way Netflix used to do it for auto-scaling. So every morning, as traffic increased, they'd ramp up the number of API servers from 300 to 650 or something like that. And then after the peak traffic in the evening, they'd ramp back down again. It's a bit lumpy, but that was basically how it worked. And then every time you want to do a code push, you pushed a new batch of servers alongside the old one, so we instantly doubled the number of servers, so you can see it added 300 servers on the right-hand side there. And then a little bit later, you'd shut down the old ones once the new ones were taking traffic. So that's kind of, Netflix has been running like this for several years. But it's kind of lumpy. You can see they bounce around a bit, there were overshoots. It was kind of a crafty way of doing auto-scaling. And one of the reasons for this, and I kept arguing with them, and they kept saying that they wanted to do this, was they were using load average as the driver for the auto-scale metric, which has these horrible non-linear overshooting problems. And anyway, so finally, they came up with a better way. It really should just use some nice stable metric like CPU usage, utilization. Anyway, so they come up with this thing called Scryer, which is predictive autoscaling. They went and looked at the history of this is the business metric, the business throughput, how many, how many people start watching a movie a second, basically, that's the graph. And you can see it's slightly different shape, but the weekends it's bulging, there's a morning bulge because kids are at home from school and they watch TV in the mornings, and during the week they don't. So you can see the weekends are different shape to during the week. So they built this sort of FFT-based algorithm that predicted what shape today was going to be for the next 24 hours. And then they used that to forward predict how many machines they're going to need in an hour's time, or however long it takes to start those particular machines' time. So this is a forward predicted driver that's basically pre-driving the autoscale minimum level. You can still have more than that, but it sets the minimum threshold. And there's a bunch of nice characteristics this has. There's a couple of blog posts describing it. So that's a fairly sophisticated algorithm, but again, now you've got whatever is measuring the system is now important, because if you have an outage in the system that's recording all of this stuff, then you get big chunks taken out of the data that's being used to feed the predictor. Right? So you have to be a bit more careful about it. They're also doing the signature analysis. So this isn't, because you're pushing code automatically at Netflix, where a code check-in causes that code to roll all the way to production, and what the barriers to it going to production are these signature analysis checks. So this is one where there's a bad signature, there's a bunch of red stuff, those little dots over on the right are way out of range. So basically they're saying, no, this is this one doesn't meet whatever. It's too bad compared to the previous code, so we're not going to automatically push that. We'll send an email to the developer to go deal with it. But if you get a nice green, happy signature with no red bits on it, it's all nice and tight distributions, then they basically say, okay, that one goes all the way to production, we'll put production traffic on it and we'll roll it around the world. And that's kind of hands-off system right now. So there we go. What's really happening here is this transition, because a lot of operations people know how to build tools to solve a problem. So there's this big focus on tools for operations people. And the problem now is that the operations are being done in a DevOps environment by the developers frequently. So what we've got is a lot of tools that are focused on systems rather than applications. They focus on utilization because it's kind of hard to figure out throughput and response time. And there's these fiefdoms. So you have a separate tool for the sysadmin, another one for the network admin, another one for storage admin, database admin, whatever other fiefdom of admins you have. And these tools don't really work across teams, and maybe you don't even have a login on all these tools. And you're trying to solve problems across this space. And they don't tend to have APIs, and they're hard to integrate and extend. And that's kind of, we're moving away from that a bit, but that's sort of the state of the art in a lot of shops. So in the DevOps world, it's much more APM-based, where you're looking inside the JVM, you're doing lots more analysis, a lot more automated tooling going on here. You're thinking about business transactions and response times and error rates, and using JVM internal metrics or whatever interpreter you're running. You're logging business metrics directly. Netflix has a thing called Servo. Yammer Metrics is used quite a lot as well. So there's a couple of tools there, links to them at the bottom. And every tool has APIs. You can extract data from them and to put them in some other tool. And deep linking means that whenever I'm staring at a page in the tool, I can take the URL and email it to somebody, and they will go to that page in the tool. Right? Not all tools behave that, particularly ones with Flash user interfaces. They make you log in and start from scratch and click 15 times to get to that page again. It drives you crazy. Embedding is a little different. It means I can take a page or a graph from a tool and embed it in a web page outside the tool. And that is incredibly useful. It makes tools viral because you create a wiki page that describes your thing, and there's like a live plot on the middle of that page that shows you the current state of it and stuff like that. And deep linking and embedding make tools go viral. So if you're worrying, if your product doesn't, or whatever tool you're working on, doesn't have enough usage within your organization, then these are some of the things that will really make it work well. Because people will start getting, everyone's looking at an outage report or something, there are links you can click that will take you to see exactly what's happening. Very important. All right, a few more things and then we'll wrap up. So there's these, the next series of challenges, dynamic, ephemeral, distributed cloud applications. So the problem is that if you're used to data center assets and you've been building tools for years, machines arrive and they tend to stick around for 3 years because you get depreciation and all that kind of stuff, and they get installed once and they sit there and they're a well-known MAC address and probably the same IP address for 3 years. And you can tie those into your tool and use that as an identifier. And cloud assets arrive in bursts. And the way Netflix does code pushes, like every 40 seconds, another wave of 100 machines gets launched. That's a single order scaler scaling up, right? It takes 10 minutes, 8 minutes. Yeah, I have some graphs somewhere, but it was a small number of minutes to deploy 500 machines. And then, oh no, that build didn't work, but it shut them all down again an hour or two later. So those machines disappear again, those IP addresses aren't seen again as those machines, and then you start another thing, and one of those IP addresses gets reused. You get this reincarnation problem, that the same IP address will appear. Sometimes immediately after you shut down an instance, it will turn up in a different instance. And this is something that happens if you have enough turnover, if you're running at scale on AWS, or pretty much any cloud. They don't blacklist it for any period of time to say, prevent it turning up. And that causes a lot of tools to get very confused about exactly what's going on. Because this machine, you thought it was one thing, all of a sudden it starts doing something else, and you missed the fact that it changed its identity. So Netflix built this thing called Edda, which is it's all Scala app. It's standalone if you've got an AWS account. And it's pluggable, so you could extend it to do other clouds. It just is like a black box flight recorder for everything that ever happened. It just sits there scraping all the described calls, logging it into a backend. It either uses Mongo or Elasticsearch as its backend, and it just builds up a history of everything that ever happened. You can say, what was the IP address of this machine last week? Or this, exactly what were the IDs of these machines at some point when there was an outage? What was the last change you had to your security group? Or those kinds of things. And once you have a full record of everything that's ever happened, there's lots of uses for this. All right, so let's look a bit at cloud-native architectures and what they look like. So this is kind of a traditional storage architecture. You've got a master-slave database of some kind, MySQL, Oracle, Postgres, whatever. Some kind of storage fabric, SAN, whatever, a bunch of storage arrays, a bunch of disks, and maybe a tape for doing backup. And then everyone's got these, and they still, they'll be around forever. And if you optimize for monitoring those, that's fine. But then they've got these new systems that look more like this. You've got a bunch of Cassandra nodes with built-in SSDs or built-in disks, and they're doing backups to a cloud object store. Right? And all of your database monitoring stuff goes, okay, where's the SQL calls, and how do I monitor this stuff, and why are there 3 copies of everything? And the copies are all spread across 3 zones, so 3 data centers. So if you're data center by data center monitoring, this turns up 3 times, so that doesn't help. So you've got to understand that you've got this distributed system that you're monitoring. So if your monitoring system isn't a distributed system, then it's really difficult to get that idea in there. So, and then if you're running one of the back-end systems like Amazon RDS or DynamoDB or one of those hosted cloud storage backends, you can't just install your monitoring agent on it. It's behind the wall, it's behind an API. So there's issues there. And you've got to basically, your tool has to integrate into the APIs that you use for monitoring these. So you go into CloudWatch or something similar. You have to conceptually think about what am I doing in things like S3, object stores, rather than just file systems. So there's a bunch of new things to worry about. And then, like I said, they span zones and regions. So the Netflix Cassandra clusters are global. Some of them are in 4 different Amazon regions. They're in Europe, East and West US, and California and Oregon, right? So you've got 4 separate regions, there's 3 zones in each region. So you've got, all your data is 12-way replicated, or in some cases, 8 or sometimes 6 way, 9 or sometimes 6. So it depends which cluster it is. Tracking that on a global basis and tracking where the traffic's going on between them and the failure modes in it is really important, but it's hard to find tooling that really understands that. All right, so just to summarize that, these are the 5 rules that I went through. Try and spend more time on analysis than you spend on data collection and display. It doesn't mean I don't want you to do good data collection and display, just don't think you're done when you get there. Try and get your key business metric latencies down less than 10 seconds. Make sure your measurement system really has good precision and accuracy, and validate it, and then you can start actually depending on it, because it's a key part of the system. It becomes part of the availability of the system is really important. you need to be more scalable and available than the system you're trying to monitor, and then optimize for these distributed ephemeral applications. All right, so that was actually finished in half an hour. It's amazing. So, any questions? And I'm appearing at a bunch of other places doing other random talks, not this talk, but doing talks on various things. Go to Q&A, and then I guess we need to get on for the next talk. Any thoughts? It's still too early in the morning.
Over here.
Yeah.
Here, can you talk a little bit about the visualizations that you said those guys are working on? What sort of stuff beyond the chart?
So if you've got every request that hits a front end goes through, a fan out of maybe 10 or 20 sub-services and sub-services, because your app is composed of these single function microservices. So if you hit the Netflix homepage app, you're hitting 30 or 40 different services just to generate the homepage. And there's this big network of requests that go out and then they come back again. So you want to be able to visualize that. But then you want to do, there is no architecture diagram anymore because everything's changing all the time. And I remember one guy said it took him 3 or 4 months at Netflix before he got over the fact there wasn't an architecture diagram. And I've seen people just keep trying to draw it, and it's just frustrating. So you just have to get over that and realize there isn't one. But if you have the tooling can show you what these flows are, then you can actually see what the architecture looks like right now, and then it will dynamically change. So the only way you get an architecture diagram is from these tools. But the problem is most of the tools don't understand zones and regions, so they just say, here's a bunch of machines, and they don't understand that your app is spread across multiple data centers, zones, and multiple regions. You've got asynchronous and synchronous stuff going on. So that's difficult. And then they don't understand that there's a large team building this. Netflix has 500 engineers roughly, order of magnitude anyway, working on all of these apps, working on the set of microservices that make everything up. And you've got these different groups. So there's a bunch of services that belong to this group, and they don't really care about everything else. They just want to see that set. So you really have to build hierarchy, and you have to tag everything. And you kind of need to know who owns everything, and then aggregate the ownership into groups, and automatically lay out everything so that if I'm in this group, I want the tool to show me just the tools that are just the stuff that's related to me, and everything else is periphery, right? So there's this kind of an aspect-oriented view into the system. I don't know. Maybe there's some visualization gurus here who can figure out how to build that stuff. I'd like to see that. I think one of the problems with open source tools is that often they end up really good backends, but not really good UIs. There are relatively few open source tools with very good user interfaces. It tends to be the professional tools that do a better job of that. One of the few I've seen that has some hierarchy is CloudWeaver, which is Linux CloudWeaver, which is a little bit like the boundary tool in some ways. But there aren't many that really are trying to figure this out. Other problem is just having an example app that is big enough and complicated enough to actually becomes an issue. Most demo apps are so small it doesn't matter. Any more?
One more question?
Yeah.
You showed a slide in there where you said you did post-commit, pre-deploy analysis on code signatures. What sort of heuristics are you using to do that type of analysis?
This typically like error rate, response time, CPU usage. You build a microservice that's a single function service, so you can just use JMeter to hit up the front of it to test it. So once it passed the functional test, the TDD kind of thing, the way that sequencing works is that and the automatic deploy system at Netflix, late last year, quite a few teams are using this. They would start 3 copies of the new code at the same time as 3 copies of the old code, and just look for differences across them, one per zone in a region. So you've got 3 old, 3 new, and you make sure they're all consistent, and make sure that the CPU usage isn't higher, and the latency isn't higher, and the error rate, that's typically it. There's a few other metrics like that, but that's generally those kinds of things. Because you've got business level metrics coming out of these systems, not just packets per second kind of stuff. Okay. All right. Thanks so much.